Hi, everyone. So today we are going to look at TikTok's architecture, and specifically, we are going to understand what physically happens, like in the real world, when a video goes viral. Now, in everyday language, going viral sounds soft. It sounds like a marketing thing, like the video just floated upward and found people. But I want you to completely abandon that mental model because, from an engineering perspective, a video going viral is a catastrophic, aggressive load event. Let's do the math right now because I think this is the most important thing to internalize before anything else. A creator films a 15-second video, it's maybe 10 megabytes compressed. The algorithm likes it, and within 10 minutes, 50 million people around the world are pressing play. Pause on that for a second. 50 million people, 10 megabytes each. That is 500 terabytes of data that needs to physically leave a server, travel through copper and glass cables, including underwater ocean cables, and arrive on individual phone screens everywhere on Earth with zero buffering in a few minutes. Now, imagine you're naive about this. You just have one big server in, say, Virginia, one database, one machine, and it tries to serve all of those requests simultaneously. What happens? The CPU pegs at 100%, the network interface card saturates, it can only send so many bytes per second before the physical wire is full, the database starts timing out because too many queries are arriving at once, and the entire app crashes for everyone on Earth. This is not a hypothetical. This exact failure mode has taken down major platforms. It's a well-documented catastrophe called a thundering herd. So the question is, how does TikTok not die? And the answer is actually three separate solutions layered on top of each other. Answer 1, decouple writing from reading. Answer 2, the push-pull hybrid. Answer 3, physically beat the speed of light. Let's go through them one by one. I'm going to draw it out. Okay, let's trace the full life of a video, from the moment a creator hits post to the moment a stranger in Tokyo watches it. Step 1 is what engineers call the write path, or ingestion, and I want you to really understand what this involves, because it's enormous. When the raw video file lands on the origin server, the server has to do a lot of work. First, it unpacks the file. Then it runs AI safety checks, scanning every single frame for content that violates the rules. This is neural network inference. This is expensive. Then it transcribes the audio to generate automatic captions. Then it runs transcoding, meaning it converts that one video file into 5 or 6 different versions. A tiny 360p version for a user on a slow 3G connection in rural Indonesia, a crisp 1080p version for someone on fast Wi-Fi, and everything in between. And since 2024, TikTok also does a round of compression on your phone before the file even leaves your hands, so less data has to cross the network at all. They've pushed part of the work to the client. This is a massive amount of compute. We're talking GPU clusters running inference on every frame of every video uploaded by a billion-user platform. The energy bill alone for this step is staggering. But here's the critical design decision. Once all of that is done, the write path's job is completely, permanently finished. It takes the finished video files, drops them into a giant object store, think of it like an enormous Amazon S3 bucket, and writes exactly one row in a database. Video 123 is ready. Here is its URL. That's it. Done. The write path goes to sleep. It will never speak to a user directly. Now, on the other side of a very clean dividing line, we have the read path, completely separate. Different servers, different databases, different scaling strategies. They never compete for the same CPU cycles. Why does this matter so much? Because the write path is expensive but infrequent. It runs once per video, and the read path is cheap but relentless. It handles millions of requests simultaneously all day, every day. If you mix them, if the same server is transcoding a video and serving it to 10 million users at the same moment, they fight each other for CPU and memory, and the whole thing collapses. The rule is simple: one system, one job. Don't mix writes and reads. This principle shows up everywhere in large-scale engineering: databases, queues, streaming systems. It's everywhere. Okay, the video is sitting in object storage. The write path is asleep. Now we need to figure out who sees it and how do we tell them. This is what engineers call the fan-out problem. One piece of content needs to reach millions of people. How do you propagate that information efficiently? Let's start small. Imagine a normal creator, 500 followers. The simplest approach is called a push model, also called fan-out on write. When the creator posts, the system immediately goes into the database, finds all 500 followers, and pushes the video ID directly into their personal feed cache, their inbox. So when follower number 247 opens TikTok, the app just reads their inbox. The feed is already built, instant. 500 followers? Easy. 500 database writes at post time. The database laughs at 500 writes. Now, what if it's not a normal creator? What if it's someone with 150 million followers? If TikTok uses the same push model, the moment this person hits post, the system attempts 150 million simultaneous database write operations. Think about what that means physically. The database has storage partitions, shards, and writes get routed to specific shards. Suddenly, all of them are being hammered at the exact same millisecond. The disks spin out of control. The write buffer fills up. Locks start blocking each other. The database cluster tips over. TikTok goes down for everyone. This failure mode even has a name. It's called a write amplification hotspot, and it's taken down major social platforms before. So TikTok does something elegant. For big creators, they flip the entire model. They use a pull model, fan out on read. When the celebrity posts, the system does exactly one database write. It puts the video ID in their outbox. That's it. Nothing gets pushed anywhere. Now, when you, one of their 150 million followers, open TikTok, the algorithm builds your feed dynamically. It quickly checks the outboxes of every big creator you follow, grabs any new videos, and stitches together your personalized feed on the fly. The key insight is this: the computational load has been moved in time. With push, the load spikes catastrophically at the moment of upload. With pull, the same load gets spread across hours as users organically open the app throughout their day in every time zone on Earth. Instead of 150 million writes in 1 second, you get a gentle, manageable stream of reads across the next 6 hours. This is the push-pull hybrid. In practice, the threshold is roughly under about 10,000 followers, your content gets pushed. Over about 100,000 followers, it gets pulled. The system makes this call automatically, per post, per creator, and you, the user, feel absolutely nothing. Your feed loads in milliseconds either way. Okay, the database is safe. The metadata is distributed. The algorithm has decided your feed. Beautiful. But we still haven't solved the hardest physical problem. We haven't moved the actual video file. And here is where I want you to think like a physicist for a moment, not a software engineer, a physicist. Light travels through a fiber optic cable at roughly 200,000 kilometers per second. That sounds incredibly fast, and it is. It's 2/3 the speed of light in a vacuum. But the Atlantic Ocean is about 6,000 kilometers wide. That means a signal traveling from your phone in Paris to a data center in Virginia, just the one-way trip, takes roughly 30 milliseconds. Round trip, 60 to 100 milliseconds, depending on the routing. And you cannot make it faster. There is no software patch for the speed of light. It is a hard constraint baked into the laws of our universe. Now think about what that means for a short video. A TikTok video is 10 megabytes. You need to start receiving those bytes and playing them within about 200 milliseconds. That's the human perception threshold for instant. If it takes longer, people feel friction. They hesitate. They swipe away. But if your phone has to reach across the ocean for every video, you're spending 100 milliseconds just on the light travel time before a single byte has arrived. You don't have 200 milliseconds to work with. You've already burned half your budget just on physics. So TikTok, doesn't fight the speed of light, they cheat it. The solution is to move the data before the user asks for it, to physically place copies of the most popular videos on servers that are geographically close to the users who are about to watch them. These are called edge nodes. An edge node is a relatively small, fast, SSD-heavy server sitting at the literal edge of the internet, as physically close to end users as possible. TikTok, through their ByteEdge network, has hundreds of these deployed globally. Now, here's the moment I find genuinely beautiful from an engineering perspective. What happens the very first time a video goes viral and none of the edge nodes have it yet? Let's set the scene. A video has just blown up. It's a genuine viral moment. Millions of people are sharing it. In the next 10 seconds, 100,000 people in Paris all see it in their feeds and swipe up simultaneously. Their phones all fire a request at the Paris edge node. Give me video 123. The Paris edge node checks its cache. Nothing. This is called a cache miss. Now, if the edge node is badly designed, it panics. It forwards all 100,000 requests directly across the ocean to Virginia origin server. Virginia receives 100,000 simultaneous video requests, each one asking for a 10-megabyte file. Virginia's network card saturates instantly. Virginia dies. But the edge node is not badly designed. It uses a technique called request collapsing, sometimes also called request coalescing. Here's what it actually does mechanically. The edge node receives those 100,000 requests. It recognizes they're all asking for the exact same missing object, so it pauses. It holds 99,999 of those TCP connections open. They're just sitting there, waiting, in memory, and it fires exactly one request to Virginia origin. Virginia sends back one copy of the file, one 10-megabyte transfer across the ocean. The Paris edge node receives it, saves it to local SSD, cache warm, and then broadcasts that single copy to all 100,000 waiting connections simultaneously. Virginia served one user. The Paris edge node served 100,000. And from that moment forward, for the next 24 hours, every person in France who watches that video gets it from Paris at 5 milliseconds. Virginia has no idea it's happening. TikTok layers two more things on top of this. First, adaptive bitrate streaming. Your phone and the edge node are constantly talking, measuring your real network throughput. If you're on fast Wi-Fi, you get the 1080p version. The moment you step into a subway tunnel and signal drops, the system seamlessly switches to a lower resolution version. No buffering, no spinner, no pause. The quality just quietly drops. When signal recovers, it quietly rises again. You never notice. Second, prefetching. While you are watching the current video, TikTok's client has already started downloading the next 2 or 3 videos that the algorithm predicts you'll watch. By the time you swipe up, those files are already on your device. The network request happened 15 seconds ago, silently, in the background. The swipe feels like magic. It is not magic. It is aggressive, coordinated pre-computation. Let's zoom all the way out and put it together. A creator hits post. The ingestion server does all the heavy lifting. It runs the AI safety checks, the transcoding, the transcription, the metadata extraction. It does all of this once in a dedicated cluster without competing against anything else. Then it drops the finished video into object storage and goes to sleep. Now the distribution system takes over, a completely separate system. It builds your feed. If you follow a small creator, their video was pushed into your inbox cache the moment they posted. If you follow a celebrity, your phone dynamically pulls their outbox when you open the app. Either way, your feed loads in milliseconds. When you actually press play, the video bytes don't travel across any ocean. They come from an edge node in your city, maybe a 10-mile round trip, instead of a 6,000-mile one. If the video isn't cached yet, the edge node collapses tens of thousands of simultaneous cache misses into a single fetch from the origin, warms its own cache, and serves everyone locally from that point on. While you're watching, adaptive bitrate streaming is silently tuning the video quality to your exact network conditions, and TikTok has already started quietly downloading the next 2 videos, so when you swipe, they're already there. This is how 1 billion people use TikTok simultaneously, and the app doesn't fall over. And here's the thing I want you to sit with. None of these ideas are individually exotic. Write-read decoupling is textbook. Push-pull hybrids appear in distributed systems papers from the early 2000s. CDNs have existed since Akamai in the late 1990s. Request collapsing is a standard caching pattern. Adaptive bitrate has been in video streaming since Netflix. The genius is not in inventing any single one of them. The genius is in combining all of them correctly, building reliable systems around each one, and making it work seamlessly at the scale of 1 billion people every single day. Every component is solving exactly one physical constraint. Compute is expensive, so decouple. Writes are slow at scale, so switch to pull. Light has a speed limit, so push bytes to the edge. Mobile networks are unreliable, so adapt the bitrate. Users swipe faster than networks, so prefetch. That's it. 5 constraints, 5 solutions, 1 system. Homework for this video. Next time you swipe and a video plays instantly, no spinner, no stall, perfectly immediate, I want you to mentally trace those bytes back. They didn't cross an ocean. They came from a machine maybe 10 miles away that had the file cached on an SSD before you even finished your swipe, and your phone was already downloading the next video while you were still watching this one. That is the engineering of the modern internet. I'll see you in the next one.